straightforward by using the volume of fluid method. Okay. So now one thing I want to emphasize that all that we have done so far, and particularly when you have multiple bubbles, you are not using what we call a discrete element method. So that we will talk about in the last talk. And as I had mentioned in the very first lecture, the discrete element method is that you basically have a Lagrangian description of each particle in a hydrodynamic description of the Eulerian flow. But if you have a large number of bubbles or large number of particles, to have the Lagrangian description combined with the Eulerian description of the hydrodynamics and the Lagrangian description of the second phase, that is a solid phase, or the bubbles, for example, which is another type of phase, it is extremely very time consuming. So whatever I have shown you is a Eulerian model, okay, or the two fluid model. So the previous video that was shown is basically a two fluid model in which you can do a lot of computation. But if you have a packed number of bubbles, a large number of bubbles, of course these approximations may not be as good, but at least for the purpose of discussion, that is what is enough. So now one thing that came up yesterday and everybody was excited about is that how does this VOF method relates to the other method, and that was the level set method, right? So I don't know whether anybody else in the audience, have heard about that or have used it. Anybody has used the level set method? Nobody has. So the people, who had done that, a little bit of that, I think they were sitting in the front yesterday and we had a very good discussion. But they are right now, I think, on their way from Banaras. So I think that they may not attend today. But the point is that level set method is an alternative. There is not much difference between the level set method and the VOF method. So now level set method, that is called LS method, is also available in Fluent, and you can simply use that. The advantage of the level set method is, some advantage is that in capturing the interface between two fluids, it is slightly accurate. Other than that, everything is the same. That is what I want to emphasize, and that is the governing equations, the incorporation of the surface tension forces is identically the same that I showed you in the previous slide. So what is done there is that if you remember that the calculation of the surface tension forces required the computation of kappa or the curvature, right? So that information that is required, because the curvature is required as the flow is evolving to calculate the surface tension forces correctly. That is the term. That term is the same. The method to calculate the entire flow, entire equations by using the simple algorithm is the same. The only thing is that instead of using the volume of fluid method, the level set method can capture the interface slightly better in some cases. Now, because everything has advantages and disadvantages, now there are methods which combine the two together. So they are called the combined VOF LS method. Okay. So they are the combined level set volume of fluid method. So people have been doing that kind of work, and all this capability is available in Fluent, but I do again want to emphasize that nothing else has changed. The simple algorithm is valid. The only thing is how do you calculate kappa. So now we have this, what is called the combined level set method and the volume of fluid method. The philosophy behind the LS method or level set method is also the same, except actually even as a matter of fact, even the governing equation, the advection convection equation also is the same with some minor differences, but those minor differences do make a difference in terms of the capture of the interface. Okay. So that is the only difference that is there. Okay. Other than that, everything is the same, and that's why the fluent has all this capability. So I am therefore going to go over quickly that what the level set method is, and then you can appreciate that how it is combined. Now the other thing I had already mentioned, and I am not going to go over again, that if you have two set of fluids and you are using a Eulerian formulation, then you have a two set of equations. So the two conservation of mass equation. So like you have L is a liquid, so this is the continuity equation for the liquid phase, this is a continuity equation for the gas phase, and again you have the momentum equation for the liquid phase and momentum equation for the gas phase. There's some line is missing here, and this is basically the interaction term in which there is a two-way approach. Remember, I had mentioned that there is a two-way approach, that is the effect of hydrodynamics on the other phase and the effect of the motion of the other phase on the hydrodynamics. So this term KLG UL minus UG is the interaction term in this equation, and as I said that one of the this for some reason is missing in this slide. So exactly this term is there in this equation. And then if you want to add the energy equation for the case of heat transfer, you can add those two equations also. So it basically it becomes a two set of equations for a liquid phase and the gas phase in multi-phase flow. So the computation becomes twice, but the methodology of solving them is identically the same. There is no difference. So that is why the algorithm or the numerical method that is there, that we have already discussed, you can apply. If you want to know a little more about it, you can just go over some of these slides, and it's straightforward. So what I want to stress here is that so this is a simple algorithm that we discussed yesterday, and that is the algorithm in which you use a staggered grid. So I mentioned about the staggered grid, and also I mentioned that you have the collocated grid that are needed to do the calculation of incompressible flow, because you have to couple the continuity equation with the momentum equation. All right. So we already covered this, if you remember. So I am not going to do this. You get this set of equations. So this is all very straightforward, and there is no need to go over this. This IPSA algorithm is now outdated. Nobody uses it. So we will not go into that. So now I want to come and show you what is the relationship between the level set method and the volume of fluid method, and they are very close to each other in the concept, but the level set method has some advantages, and that's why people are a little bit excited about it. And the advantage is that it can capture the interface slightly better. Okay, but on the other hand, VOF method, which is an older method, also has the advantage. So now people have combined the best feature of the two, and that is called the combined LS VOF method. So it will become clear how it is done. So what happens in the level set method is like if you remember the advection convection equation that we had for alpha, right? What was that? It was d alpha dt plus u dot gradient of alpha is equal to 0, right? And that equation, when we solved by simple discretization, then that equation gave you a solution of alpha, and from that solution of alpha then you could calculate kappa, and that goes into the momentum equation to include the surface tension. That's simple as that. In this case, again, we define a function which is called a distance function. Okay, it is some kind of a mathematical construct. It doesn't have any physical meaning. It's simply a mathematical construct. Actually, in a VOF method, alpha has some physical meaning. In a VOF method, what is the physical meaning of alpha? Pardon? Go ahead. Go ahead. What is that? Yeah, volume fraction. That's what I'm saying. So so that has a physical meaning. In this case, in a level set method, P is or phi has no physical meaning, except it has some way to characterize the interface. And so this is what is called a distance function, which means that at the interface this distance function defined by phi is equal to 0. And on one side of the interface the phi is negative, on the other side of the interface phi is positive. But the equation that governs the phi is identical to the equation that governs alpha. So what that equation will be? I have not shown you. That will be d phi dt or d phi dt plus u dot del of phi. So what you do there is that if you calculate this, then you can show that if you can solve for phi, then the gradient of phi is related to kappa, and then if you can know that how to use that, then of course that is what you need for the surface tension. So they are very much related, but it turns out that although it is a non-physical quantity, it is only a mathematical construct. In many ways, the conceptually it is the same. Why it gives you a better description of the interface? Now, in the interface description, as I mentioned to you, you had a sharp surface method in which the delta function goes to 1, but the implementation was difficult. You see, mathematically, the sharp surface method in which delta goes to 1 exactly at the surface gives you the most crisp answer. The discussion that we had yesterday was how do you implement it so that it is exactly equal to 1 and everywhere else is equal to 0. So again, in that context, it turns out that if we go with the level set method with a similar kind of equation, there are some fudge factors, means there are some approximations you can make for the delta function, that it doesn't give you a very sharp interface, but it gives you a smooth interface. All right, it doesn't have the possibility of any kinks and other things. So there are two other equations that are interesting in this context and that improve this method, and they are similar equations. One of them is the variation of the density that can take place along the interface. So in some cases, when you cross the interface as a single point, of course density has to be different, because on one side there is air, other side there is a water, let us say, or it is gas and there is a liquid. Now similarly the viscosity is different, but as you move along the interface, you will find that at each point of the interface the density and the viscosity is different. So in this particular method, you can also allow the change or variation in the density as well as viscosity along the interface with the same type of advection convection equation. So this is other advantage that comes into the LS method or level set method. So again, as I mentioned, the equation for this distance function is the same, and that is the phi of time derivative plus u dot gradient of phi. So then again the calculation of this particular advection convection equation is what? Is the same procedure that we did for alpha. And then the integration of that for including into the surface tension term in the momentum equation is identically the same. And the entire set of equations are solved numerically by the same method. And what is that method? The simple method, simple algorithm. So the only thing that we are changing, everything is fairly identical, and that is very interesting between VOF and LS. That one is the physically we have a different interpretation, but also the way we treat the delta function becomes different. But physically there is one more important factor, and that is it allows for the variation of density along the interface as well as the variation in the viscosity along the interface a little more accurately than we could do otherwise. Only a little more accurately. It may not be a major difference, but in some application it might make a difference. What is the application where it may make a big difference? For example, if you have a thin film of a very large viscosity. So you have a thin film of a very large viscosity. Let us say that film is made of oil, which is much larger viscosity, and then on that film you have a drop of water hitting it, which has a much less viscosity, then this will give you a slightly better accuracy. That's all. Other than that, there is not much difference between the two, and methodology is the same, because the discretization that you carry out on the interface is similar to this equation, and in the case of other one is alpha t plus u dot del of p. So now again, there are some changes that these are shown here, because I said that phi is a distance function and it has no other meaning except is a mathematical construct. So if phi is equal to 0, you have some value of the density. If phi is less than 0, it is a other value of the density, because as I said, phi is exactly equal to 0 at the interface, and if it is greater than 0, it is one phase, it could be liquid for example, and if phi is less than 0, it is other phase, and then we assume that at the interface it is basically the sum of the two. Same thing we do for the viscosity. So that is the one that allows you for this variation. So now it turns out that again it is not possible to capture it crisply. So you allow for this first factor, that is epsilon. It's a small number. So this epsilon could be 10 to the power minus 2, minus 3, whatever you feel like. It's a very small number. So it turns out again that you can choose that instead of phi greater than 0, it is phi is equal to a very small number. So if it is a small number, then you are very close to the interface. If you make it a big number, then you are far away from the interface. So in order numerically, the purpose is only numerical. So then you choose a small number like 10 to the power minus 3, minus 4, and so you are on two sides, on a gas side and the liquid side, and then the average here becomes this, and this is again a fudge factor. Now if you ask me why are you using this sine function and all that, and why are you doing this, this is the way people, when they did the calculation in the actual implementation, they found that this kind of adding some these empirical functions was useful. That is the only reason. If you want, you can use maybe some other function, cosine function, algebraic function, but it turns out that this was the best one to do. Okay. So now you have this definition of rho, and same thing you can do for the definition of the viscosity to allow for the variation along the interface of these two variables. Okay. So now this is the same term in the momentum equation. If you recall, this is the surface tension force, this is the surface tension coefficient, this is a kappa, and this kappa now previously was a function of alpha, that is the volume fraction. Now it is a function of this distance function, and other than that it is the same expression that we had before. But now the thing is that this delta phi, which is a Dirac delta function, where it could acquire a value of 1 in a sharp interface, now it is dealt it like this. So epsilon and minus epsilon, they define at the interface a slight distance, okay, whether you are in a liquid or you are in gas. So if it is minus, it could be a liquid, and it is plus, it could be a gas. But what happens is that in order to make the calculation a little bit simpler, but still have a smooth capturing of the interface, you assume that delta phi is this particular function. Okay. This is the approximation to the delta function. So if you look at it, this is a smooth delta Dirac delta function that is being used. So otherwise, with these some nuances that I am showing you in the method, that is the LS or the level set method, they are fairly close, they are fairly same to each other. And again, please understand that this phi is, which we will call a distant function, is nothing but a mathematical constant. It is not any physical quantity that we had in VOF. Okay. Now the discretization is identical that we showed before. for d alpha dt, that is the VOF method, and you again do the same kind of a discretization on the grid at I plus half and I minus half in order to integrate it into the methodology of the fluent using this simple algorithm. So, again you do the same thing, the upwinding that we did before in the fluent calculation, you can use a higher order discretization. So, there is nothing new here. If you want to go over, you can, I do not want to spend time here, but this is absolutely identical than this scheme and so on, which shows us some more better way to do it. Now, in any of these cases, if you are going to use this method and you are going to calculate the interface using phi, you have to have an initial value, right? In any calculation that you do for advection convection equation, you need a initial value. You need an initial value for alpha also. So, what was your initial value for alpha? Anybody remembers? 0, 1, and the method, the way we described it, what was called PLIC, and that is the piecewise linear approximation. So, here there is a slightly different way of initialization of phi, but it is conceptually the same, because phi is 0 at the interface. So, the initialization is slightly different in terms of the epsilon that I showed you. Okay. And so, this is shown here, how do you do the initialization by using this kind of a construct, and these are all empirical functions that people have worked on. So, the fundamental work in this area is that of Sussman and Puckett. So, there are two papers that are important in this entire discussion if you want to go back to the basic paper. One is a paper by Hurt and Nichols for the calculation of alpha, and the other is the paper by Sussman and Puckett for the calculation of phi. Okay. And then there is another paper by Setian, but you do not have to worry about that. Okay. So, if you only focus on these two papers, go over those papers, then you will understand completely the theory behind the level set method and also the method of volume of fluid. And they are very basic papers written long time ago, and there have been lot of changes and improvement. The contribution here and the discussion that we had yesterday versus today is primarily based on the fact that how do you integrate in the framework of the fluent to model the surface tension term in the momentum equation. Okay. So, that is a very brief line to understand that why are we doing it. Okay. So, again solution sequence is identical what we did before, is just written there. How do you do this? And then you can couple the both level set method and the volume of fluid method, because there is an advantage of one of them over the other. So, because in one case you see the level set method, it turns out that after you do the calculation, there is a little bit inaccuracy in the calculation of the mass transfer. So, you lose mass, but get a very better shape of the interface. In the VOF method, you conserve the mass, but the curvature calculation can be slightly choppy and not very smooth. So, if you combine the two together, the best features, then it is what is called the coupled level set and VOF, or CLSVOF. Okay. And then again, this is again I have brought it back in the combined method. This is the alpha, which is identical to the phi equation. So, now instead of solving one equation, you have to solve two equations by the methodology that I described. So, you have the same advection convection equation for alpha, and you have same advection equation for the phi, and then you combine the two together and go through the procedure. It makes it a little more complicated, a little more difficult, but as I said, you can have a more smoother capturing of the interface with a better accuracy of the mass transfer or mass conservation across the interface. Okay. So, again these are the steps that one has to go through, and it turns out that I just want to mention this. Here is the kappa. Okay. Now, kappa is the one that we need for the surface tension term, and what is n in this case? Can you guess what is n for the level set method? No, it is a normal vector, but how do you define the normal vector? We have got a calculation from the level set method, what calculation that gives you phi or phi, right. So, how do you define n in terms of phi? Huh? That is correct. So, it is delta phi divided by the modulus of delta phi. I just wanted, that is missing here, but I wanted you to know, and if you want to write down in your notes, that is an important point, that how it is related to the solution of phi. Okay, that is it. And then again, this is showing a relationship, and this is again some kind of empirical relationship developed by trial and error, that you can see that epsilon is a little value that you specify as a user, 10 to the power minus 3, minus 4, whatever you like, and then this is phi, and this is a sine function that I showed you before, that was also included in the description of rho and mu, and same sine function is being brought in here. What it shows is the relationship. That is what I want to emphasize. What it shows is the relationship between phi and alpha. Okay, and this relationship between phi and alpha is given by this empirical relation. Okay, this is what I want to show you. This is the final close relationship that I am trying to say. So, if you want to calculate by two equations that are given, and that is d phi dt plus u dot delta alpha, and the other one is delta phi, and the other one is d alpha dt plus u dot delta alpha. We solve these two equations, and of course, any time you solve an equation, you have to start with some initialization, and then these two are related by this relation. Now, you may ask this question, where did you get this relation? I do not know the answer to that, okay, because this is based on the trial and error that Sussman and the co-author did, and other people did that, and this is not a unique function. This could be a different function. So, here you can see that if epsilon is 0, then of course, you have phi, but this will not be, you will have to then put this thing is on this side, because otherwise this will become infinite. Then what would it give if epsilon is equal to 0? It means that phi will become equal to alpha, which means that you are capturing the distance function which is equal to 0 at the interface, and you are also capturing from alpha the very sharp interface. Okay. So, this is a very, very close relationship, but what the contribution of people in that particular paper that Sussman did for the distance function, and actually a much more profound work was done by Setian, is that they said that this method, by having this mathematical function which is called a distance function phi, you can do a not only a problem in the multiphase flow, but in variety of other cases where there is a deformation in mathematics of different shapes by changing the topology, they call. So, there is a field of topology in mathematics where you can twist around and make all kind of very, very funny shapes by whose mathematical description is extremely hard. Okay, like you have a donut, you know how to describe this. But suppose you have a twisted donut, it's very difficult to describe mathematically how a twisted donut will look like. So, what they said is that you can describe these very, very complex topological shapes in mathematics by describing this distance function, and then trying to describe the advection convection equation, and then imposing the correct boundary condition, so that you can then come up with some approximation for this particular shape. So, that is where this method actually originated, but then people found that this is very useful in the context of multiphase flow and is related to VOF, and then it is almost identical, as I told you, with some small differences. So, if they combine the best features of two of them, then you can get smooth interfaces, and then also you can conserve the mass flow conservation property across the interface. And so, now, but the disadvantage of it is that you will have to solve two set of equations. Okay. So like, in my work and that of my students, we really don't want to, unless until there is need, we never found a need to combine the two together to solve this. So we have always solved our almost 99% of the problems by using VOF. We found that it works extremely well. It really does a very, credible solution, and that is good enough for engineering purposes. But this is the final relationship I want to show you, that is the phi is related to alpha, and this is not a unique relationship. Okay, you can have a different one, you can choose your own, you can come up with your own. And this is of course some more details which are not relevant, and the kappa that goes into the solution of the momentum equation is derived by this equation, where n is given by the delta phi divided by the modulus of delta phi. Okay. So this is the two papers which are very important, that is of Hurt and Nichols, and the other one is Sussman and Puckett, and there is a variation of that, Voset by Sun and Tao. And if you just put it, all these names, into the Google, you will find enormous information. You can also go to the Wikipedia and you will find this lot of information. So you will find that if you just are more interested in this, as I said, Sethi and Rosher have done that, the same people, level set method, in the context of topology in mathematics. But for our purpose, the key papers to study, if you use the front tracking, is by Tregarson, the volume fluid method is Hurt and Nichols, and the level set method is based on the Sussman and Puckett. And the other thing I want to point out is that for all practical purposes, two things to remember here in this whole lecture, and that is the only change that we have made to account for the interface effect is inclusion of the surface tension term in the momentum equation. The rest of the methodology of simple algorithm is completely valid. Okay, there is no other change at all. All right, and so you don't even have to know that what is inside the code. It is so automatic that you can just specify that this is what you want to do and initialize the data, and it will calculate a bubble, for example, in bubble of gas or air into a liquid. Now, if you have more complicated cases, which I showed you, that you have these thousands and thousands of bubbles into the water. Okay, that is a second aspect. You cannot take an individual bubble, and then you try to chase that bubble by the Newtonian law of motion, because you will be working on that forever. So in that case, you treat this as a Eulerian method, which means that the motion of the liquid as a hydrodynamic equation will be governed by one set of equations, that is continuity and momentum, including the surface tension effect, and the motion of all the bubbles together will be treated as another fluid. Okay, I mean, it will be treated not as individual bubbles, but as another fluid, which is governed by the second set of equations of conservation of mass and conservation of momentum, including the surface tension term. Okay, and the entire methodology is the simple algorithm. And I also showed you the relationship between the level set and the VOF. So I think that I want to conclude this here. I have skipped a lot of slides because my feeling was, when I was looking at this afternoon, that we have a lot of material to cover, and so I should only emphasize on the key points. But I think I do encourage, and I do like to have a discussion. I think I had a lot of fun having discussion yesterday, towards the end, and I think that kind of a discussion is very useful also. It was very exciting, to see how are we thinking and how we can, have some kind of, interesting, dialogue that can clarify some of the things and some of the way we think about problems. So I think at this point, I will encourage you to ask any questions that you may have about whatever we have covered on this lecture since yesterday. Epsilon is a user input. Yeah, I mean that I do not know how much it will increase, but there is a disadvantage if you have too large a value and if you have a too small a value, because what happens is that at the interface phi is equal to 0. When phi is equal to plus epsilon, then it defines a liquid, and which is minus epsilon, then it defines a gas. So if epsilon is say 10 to the power minus 5, it is like a convergence criteria. So then what happens is that you are very close to the interface, so the sharpness will increase, okay, because we are no longer using the delta function, we are using a approximation to the delta function, okay. But if epsilon is equal to 10 to the power minus 2, then of course the sharpness will be slightly less, but certainly you cannot use epsilon is equal to 10 million. You see what I am saying? Because the purpose by the very symbol itself, it indicates that it has to be a small number, okay. User input, yes, that's a good question. Yeah. So what is recommended is that is based that how do you choose an epsilon? You always have a grid, and the grid has some value of delta x and delta y. So it is what is basically saying is that instead of choosing too small a value like 10 to the power minus 6, it may give rise to some convergence problem, I am not sure, all right. And then if you choose a very large value, then of course it can have a interface which is not going to be crisp. So this may be a recommended value that it is based on the kind of grid that you have. Well, why it is high? Because if your delta x is very small, then it will be small. You cannot choose delta x to be 2, right? Because you see, in any grid that you have, the truncation error is of the, in a second order method, truncation error is delta x square. So if you are going to choose even delta x is equal to 0.5, the truncation error is 0.25. So even in a normal course of things, whatever you may be doing, even in one dimensional problem, you will choose delta x is small enough, so the truncation error is small enough, okay. I mean this is just comes from the simple, like Taylor series expansion where delta x comes in, is assumed that delta x is so small is almost close to 0, right. So delta x qualitatively has to be small, and if it is very small close to the interface, it has to be small because to capture that. So then I do not know what it should be. It should be 10 to the power minus 2, minus 3, and you multiply by 1.5, it does not make a difference. If you do not like the 1.5, you can drop it. But you have a good point. I mean, I am not questioning the observation that you are making, but again the interpretation of it, that is what I told you. Okay, any more questions on this? Yes, sir. In which method? Oh, I mean, in an Euler and Euler method, and if you have this, it is done exactly the same way that we had in the previous momentum equation that I showed you. That is correct. The addition of the term is the same. The method of discretization is the same. No. What I am saying is that I just mentioned to you that if you have, for example, a large number of bubbles, which one example, right? And you have a large number of bubbles made of air, and then you have a liquid. In that particular case, the large number of bubbles that you have, you will have to treat them as a separate fluid. Okay, although they are bubbles, but you will have to consider it as a separate fluid. And then you have the other one that you have a separate fluid. So in that case, you cannot consider the way we have been trying to deal with the with a single bubble in a liquid with a surface tension. It doesn't make sense. So you are completely right about that. So you have to see what problem you are doing. But suppose you want to apply the same method, and you have, say for example, 2 bubbles or 5 bubbles. In that case, if you want to consider their motion, then you will have to make sure that both of them have a, it could be even the, what I showed you, the term K, the term K in which you have exchange that is taking place of momentum. So all these things they are due to model the way you are, model based on the problem that you are looking at. So maybe with the way when you are completely right that if you have millions of bubbles, then there is no need for using that the surface tension, because you don't know how to define that.